We'll continue in this lecture with the remaining modulation techniques and one as shown in the following figure. So this shift in phase by 180 degrees can be represented by the following scale, while one represents the in phase symbol and -1 represents a symbol that is shifted in phase by half a cycle. The essence of quadrature modulation methods is the application of complementary pairs of amplitude to two simultaneous sinusoidal waves differing in phase by 1/4 of a cycle. So now we have a shift in phase by 1/4. This description is a lot to absorb in one go. So let us think for a moment just about sinusoidal waves that are 1/4 of a cycle apart. Sinusoidal waves with a phase difference of a quarter or 3/4 of a cycle are said to be in quadrature phase relationship. It's customary to refer to one of these waves as the I wave as represented in the following figure, or in phase wave, so the ones that start from 0, and the other as the Q wave or quadrature wave as shown in the second figure, part B. So I wave is in phase wave and Q wave is a phase shifted by quarter a cycle. Sinusoidal waves in a quadrature relationship have a special quality of independence from each other that makes them very useful in carrying data, as you will see in the coming slides. One of the features that make them useful is that if either or both of the waves is multiplied by -1, the resulting waves still have a quadrature relationship. For instance, if I take the I wave of part A of the previous figure and multiply it by -1, the result is the figure that shows a quadrature relationship with the original Q wave, as you can see in the following figure. So it's a convenient way to represent the symbol available when both I and Q waves are modulated separately using 2 dimensions rather than the 1-dimension line of QPSK representation. There are 4 symbols with QPSK, whereas QPSK has only 2. We have one X where the 2 symbols are represented in QPSK because we have half a cycle difference in phase. But here in QPSK we have quarter phase different in phase, quarter cycle difference in phase, and this could be represented by in 2 axes, where on each X, I, and Q we have 2 orthogonal symbols. Sorry. In the first constellation diagram that we have just presented, the symbols lie on the axis, indicating that each consists of a pure I wave or a pure Q wave. Alternative constellation, the symbols lie off the axis, indicating that combinations of I and Q waves are used to represent each symbol. In fact, each symbol uses the addition of an I wave and a Q wave, each of amplitude +1 and or -1, giving a total of 4 possible symbols. This arrangement is the one used in practice for reasons of technical implementation. If multiple pairs of Q and I amplitude, say 1 and -1 and 3 and -3, are allowed, then more symbols become available. This is the principle of quadrature amplitude modulation, or QAM, which you can think of as the application of ASK to QPSK. Three-bit binary words are used in case of 8 QAM, because in 8 QAM we have 8 symbols and 8 equal to power 3. This means that we can have each symbol represent 3 bits. Since we have 8 combination of 3 bits, and each combination could have a unique symbol to represent it. And so on for the remaining version of QAM as 16 QAM or 64 QAM. So for 16 QAM we have 16 symbols which are in quadrature phase as shown in the following figure. We are changing either the amplitude or the phase when we are going from one symbol to another. And in 16 QAM we'll have 16 symbols, so 2 to the power 4, and thus we will have 4 bits per symbol. Since we have 16 combinations of 4 bits, so each combination of 4 bits will have a unique symbol that represents it. So this orthogonality in the context of data communication implies independence. So when we say we have orthogonal symbols, so we are meaning that we have independent symbols. Orthogonality literally means at right angles, but that does not explain what is special about the I and Q waves. If the point moves parallel to any one of the 3 axes, one of the x, y, or z coordinates will change, but the other 2 will remain the same. A point's position relative to any axis is independent of its position relative to the other axis. If the axes were not orthogonal to each other, this would not be true. As you can see in the following figure, the I and Q waves can be represented as orthogonal phasors. The diagonal of the rectangle created by I and Q is the phasor of the symbol that is transmitted. Let's start with the new section, which is about spectral efficiency. Whenever a carrier wave is modulated, it has a wider frequency spectrum than when it is unmodulated. So when we modulate the baseband into a carrier wave, we will have a modulated signal which has obviously a wider frequency spectrum, which occupies a wider frequency channel. It means the width of the frequency spectrum that the communication channel occupies is, roughly speaking, its bandwidth. We are using bandwidth here in its pre-digital sense, where it refers to a range of frequencies rather than its more recent sense of the capacity of a digital communication channel, that we will talk about it in Shannon equation later on. In principle, higher data rates can always be achieved using more of the frequency spectrum by having a wider bandwidth. Spectral efficiency is a performance measure of how well a data transmission system uses the frequency spectrum. An efficient system being one that uses relatively little of the spectrum while still giving a useful data rate. Spectral efficiency is measured in bits per second per hertz. So the higher the number of bits per second per hertz, the higher the spectral efficiency, the more efficient the usage of spectrum. This means that 800 kilobits per second divided by 0.02 megahertz. To have correct division, we should transform the frequency band into kilohertz, because we have kilobit per second in the numerator. So we'll have 800 divided by 20. It's equal to 40 bits per second per hertz, and since A has 20 and B 30 and C 40 bits per second per hertz, so the case of C has the highest spectrum efficiency, while it has not at all, or it has minimum bit rate comparing to the two previous cases. So the spectral efficiency is very important to be considered when comparing between the performance of the modulation technique. Another thing to take into consideration is intersymbol interference, ISI. So take the case of figure B, shows that the 16 QAM constellation diagram occupying the same space of the QPSK system presented in figure A. Notice that the points are much more densely packed in figure B, indicating a greater spectral efficiency. So in part B, we could have more bits per second per hertz, since we have more densely number of symbols and thus more bits per symbols. This can be a drawback on the other hand, because one of the effects of noise is to shift the constellation points increasing the likelihood of one symbol being mistaken for another. So the closer the symbols to each other, the probability of error becomes higher, since the noise would affect the receiving position of a symbol, and that could be interpreted as another symbols, and this is called intersymbol interference, and this will lead to demodulate the symbol as another bits, and this increases the bit error rate. Now we'll start with the section of power spectrum, noise, and data rate. As we have seen, a modulated carrier has bandwidths that occupy spread of frequencies rather than a single frequency. So the power transmitted is distributed across a spread of frequency over the channel band. This fact has a bearing on a number of important considerations for a practical wireless system, such as the immunity of the signal to noise and the maximum rate at which data can be transmitted. Wireless transmitters vary greatly in output. Ranging from several kilowatts or megawatts in the case of national radio and television transmissions to a watt or a fraction of a watt in case of a Wi-Fi access point. An access point is the part of a Wi-Fi network that relies data between the mobile device and links them to the wired part of the network. The 2.4 GHz band used for Wi-Fi and Bluetooth, although free for non-licensed users, is not unrestricted. Transmitters on these bands are required not to exceed maximum allowed transmission power. In Europe, the maximum allowed power output is 100 milliwatt. In the USA, the maximum power output is 1 watt. The way the radiated power is spread across the bandwidth of the transmission is apt to be non-uniform. To simplify the analysis, I will assume the power to be spread uniformly across the bandwidth of the transmission. The following figure shows my simplified representation of the power distribution for a device transmitting on a channel frequency in the 2.4 GHz. By making the power distribution rectangular, we have effectively assumed that the power is distributed evenly over a band of frequencies and does not exceed outside that band. The total power within the envelope is 100 milliwatt. I remind you that this is not the case in practice. The vertical axis in the figure is labeled power density. You have met this before, but I have not said much about what it is yet. Power density is a measure of the concentration of power in relation to frequency. For example, a power of 10 watt distributed across a continuous band of frequencies 100 Hz wide gives a great power density than if distributed across a band 10 kHz wide. With a rectangular distribution like this, like the one shown in this figure, the power density is simply the total power divided by the bandwidth. In this case, the bandwidth is 20 megahertz. Hence, the power density within the envelope is 10 milliwatt. So, times 10 to the power minus 3 to express it in watt, divided by 20 megahertz, and times 10 to the power x to express it in hertz. The ratio will be equal to 5 nanowatt per hertz or 5 milliwatt per megahertz. By the time the signal reaches our receiving device, when it reaches a receiving device, the signal power will be much reduced, of course. The receiving device will receive not only the intended signal but also noise. Noise too has a power distribution. As there are many different kinds of noise, there are many different kinds of distributions. Commonly encountered type of noise is so-called white noise, which has a flat power spectral density over a wide part of the frequency spectrum. Theoretically, the white noise is flat over the entire frequency spectrum. The ratio of signal power to noise power at a device significantly affects the rate at which data can be transmitted. The signal to noise ratio is found by dividing the signal power by the noise power. The larger the number, the better, because that indicates the signal power is greater relative to the noise power. 2, I think, if we multiply this by 20 to 30, 300, it will be equal. We must calculate it, but it will be the answer will be less than 3 in case of receiving device C, and in this case we can see that the signal to noise ratio of receiving device C is the minimum, has a minimum value. This means the other ones has a better reception. Let's see the notion of spectral mask or spectral envelope. Many wireless communication standards define a spectral envelope or spectral mask within which the power spectral density must lie. Take the case of the spectral mask of 802.11b standard. It has the following form. Of course, it could have another form for another standard. So the frequency values on the horizontal axis represent how far in megahertz you are from the channel frequency. So the 0 in the x-axis refers to the channel frequency, and we are putting 0 because we don't have one channel frequency, but we have multiple ones. So to have a general representation of the spectral mask, the central frequency is represented by 0. The vertical axis is relative power density in decibel. It is relative rather than absolute because no maximum value is laid down for the power density, except in Japan. So different transmitters will have different maximum values. If the maximum power density is, say, 10 milliwatt per megahertz, which happens to be the maximum allowed in Japan, then in the figure, the 0 on the vertical axis represents 10 milliwatt per megahertz. The part of which a width of 22 megahertz marked by the region A tells us that this power density of 10 milliwatt per megahertz cannot spread more than 11 megahertz on either side of the channel frequency, represented by 0 in the spectral mask. We can also see that if the maximum power density is 10 milliwatt per megahertz, the maximum allowed power in the 22 megahertz wide region is 10 milliwatt per megahertz times 22 megahertz. This will be equal to 220 milliwatt. In the frequency range between 11 megahertz and the 22 megahertz from the channel frequency marked B, the power density must be at least 30 dB below its maximum value. A decibel value of minus 30 dB corresponds to a fraction of 10 to the power minus 3, so that power density in this zone cannot exceed 10 milliwatt per megahertz divided by 10 to the power 3. This is equal to 0.01 milliwatt per megahertz. So if the maximum value is 10 milliwatt per megahertz, the power density in region B will be 1000 times smaller, because minus 30 dB, and this will be equal in this case to 0.01 milliwatt per megahertz. If we want to calculate the total power in B, in region B, so we must multiply 0.01 milliwatt times 22, because we have 11 from one side and 11 from the other side, and so we have 22 as total power in region B. So times 22 megahertz, so we'll obtain the total power for region B in this way. The 44 megahertz wide zone, there is no limit to how widely the transmission can spread along the frequency axis. So we can take another exercise for the same spectral mass to calculate the power density would be allowed outside the 44 megahertz zone, part of C4 device with a maximum spectral density of 5 milliwatt per megahertz. So 5 milliwatt per megahertz is a maximum power density, so it is represented by 0 dB in the vertical axis. So in region B, which is minus 30 dB smaller than the maximum value, this means 1000 times smaller than 5 milliwatt per megahertz, so it will be 5 microwatt per megahertz as power spectral density, and for region C it's minus 50 dB. This means that it is smaller by 10 to the power minus 5, so we will have 5 times 10 to the power minus 5 milliwatt per megahertz. As we have said, we don't have only one channel in case of T324 That's why we are representing the channel frequency by 0 in the spectral mask. However, in these standards we have more and more channels. So the first channel has its center frequency in 2412 megahertz, and the rest of channels are spaced by 5 megahertz higher. So if the space between the channel frequency is 5 megahertz and the channel bandwidth is 22 megahertz, this means that we have adjacent channels have overlapping paths between each others. Please note that not all the channels are available in all countries. The USA uses channels 1 to 11. Europe has 2 additional channels at the top, but these are not available in all parts of Europe, nor are all the lower ones. Note that the lines for channels 1, 6 and 11 do not overlap each other. So if we have 5 megahertz spacing between adjacent channels, so if we have 5, if we are using in the same proximity 2 channels which are spaced by 5 channels to each other, in this way these channels will not be overlapped. So if we are using channel 1, the remaining channels that do not overlap on channel 1 is 1, 6 and channel 6, for example. And if we are using channel 1 and channel 6, the channels that do not overlap with these 2 channels is channel 11. So 1, 6, 11 spaced by 5 channels will not have overlapping parts. If we use channel 2, we can use as second channel, channel 7. So and so on. If we are using channel 3, the second channels that do not overlap is higher or equal channel 8, and so on. Let's start to explain the Shannon equations. It's very interesting equation for calculating the channel capacity bit per second. So basically noise can affect the data rate. In digital communication, the effect of noise is to cause zeros to be randomly misinterpreted as 1 and vice versa. A certain amount can be done to correct these misinterpretations by incorporating error correction within the message. But as the signal to noise ratio deteriorates, more and more error correction data needs to be added to overcome the effects of the noise, and less of the data transmitted data consists of the original message. The information rate measured at the rate at which the message is transmitted suffers. Shannon has established in 1948 that there is a three-way relationship between channel capacity, bandwidth, and signal to noise ratio. One of his discoveries was that signal to noise ratio and bandwidth can be traded off against each other to some extent. That's to say, if the bandwidth of the transmission is increased, a worse signal to noise ratio can be tolerated and the same data rate maintained. If we are prepared to sacrifice data rate, then we can tolerate reduced bandwidth or a worse signal to noise ratio. Shannon expressed this relationship mathematically as the following. C, the channel capacity in bit per second, is equal W, the bandwidth of the data in hertz, times log base 2 of 1 plus SNR, which is signal to noise ratio, S divided by N, total signal power divided by total noise power. Log base 2 of 1 plus SNR can be expressed as a function of S divided by N in the following figure. So this logarithmic scale of signal to noise ratio plus 1 could be either read from the curve or calculated using a scientific calculator. The graph indicates that with a signal to noise ratio of 10 to the power 6, the term log base 2 of 1 plus SNR has a value of 20. So we have a logarithmic increase, of course. So it's a considerable increase of a signal to noise ratio will have a small increase in the log, and so in the channel capacity, and not of course as linear increase. So the theoretical maximum data rate at this signal to noise ratio is 20 W. If W had a value of 0.5 megahertz, if the channel band is 0.5 megahertz, for example, the theoretical maximum data rate would be C will be equal to 20 times 0.5 is equal to 10 megabit per second. Approaching this rate might require extra bits to be added for error correction and sending the data stream faster than 10 megabit per second, but 10 megabit per second is the maximum rate at which data can be recovered error-free. If you use the curve to read the value of log in case as an r is equal to 10, so you can see that it is around 3.5. So log is around 3.5 and times W, which is equal to 5 megahertz, and in this way we can calculate the maximum data rate. So if we are 7 meters far from access point with the intervening external stone wall, the signal to noise ratio has relatively low values and between 1 and 10. And when we go or move toward the access points with less number of obstacles, the signal to noise ratio will be increased, and it could be increased relatively, as for example 1.5 meter from access point we could have 10 to the power 6 as SNR, and a few centimeters far from access point we could have 10 to the power 8 as SNR. So to increase the data rate, this could be achieved by increasing the signal to noise ratio, as we have said, or broadcasting a more powerful signal will improve the signal to noise ratio in this case. However, there are drawbacks with this approach to increasing data rate. One problem is that increasing the power output risks causing interference with other communication systems using nearby or related frequencies. Another problem, more important with high power transmitters than with low power domestic system, is that increasing the radiated power can considerably increase the running cost. So increasing the bandwidth W looks as though it will increase C. However, increasing the bandwidth can worsen the signal to noise ratio. For example, if we double the bandwidth while keeping the signal to noise ratio constant, the C part of the S and R stays the same. But if the noise has a constant spectral power density and will double, the net effect is to hold the signal to noise ratio. However, as we have already seen, there is not a proportional relationship between C and SNR, but logarithmic relationship. The signal to noise ratio can vary widely and have a relatively small effect on maximum channel capacity. So increasing the bandwidth is a good option for increasing the maximum channel capacity, even though its effect might be offset somewhat by worse signal to noise ratio. This is the theory behind ultra-wideband methods of transmission, which, as the name suggests, use an extremely wide bandwidth to achieve high data rate. Just increasing the width of the channel by itself is not enough, of course. The modulation method needs to be adapted to explore the extra bandwidths. Spread spectrum methods are one way to do this.